Excuse me.
Okay.
Hello, sir.
Yes.
Yeah. No, sir. I was just giving a reminder to start the recording, but you have started.
Yeah. Can you see whiteboard?
Yes, sir.
Yes.
All right. All right. So this is our lecture number 2, and here I'm going to start nth order linear differential equation. So I'll start with the unit number 1. Nth order linear differential equations and applications. Okay, so what do you mean by a linear differential equation? So it's a definition. A differential equation which contains differential coefficients, and the dependent variable in first degree degree means power. Yesterday we had seen some examples, right? Does not involve the product of derivative with another derivative or with dependent variable and in which the coefficients are constant, and this is also important, and in which the coefficients are constant is called as linear differential equation. Very long sentence we have. A differential equation which contains the differential coefficients means derivative dy by dx, d2y by dx squared, second order, third order, and dependent variable, let's say y, in first degree. So first degree means yesterday we had seen the power, whatever the power we have, it is 1, not more than 1. Okay, and does not involve the product of derivative with another derivative. So for example, dy by dx into dy by dx, so that will be what, dy by dx whole square. So this is not allowed, right? Means here in the first sentence you can see first half dependent variable in the first degree, like that derivative also of derivative operator is also of maximum degree is 1, right, of each term, and does not involve the product of derivative with another derivative or with dependent variable, means something like this, y dy by dx or y d2y by dx square. This is not allowed because this is dependent variable, because y depends on x, and this derivative d2y by dx square into y, this product is also not allowed. Okay, and in which the coefficients are constant. So all coefficients are constant, that's why we are calling this as a linear differential equation with constant coefficients. So for example, so let me give some examples. Yesterday already provided. So here we have some examples. Example number 1, d2y by dx square plus 2 times dy by dx plus 5 times y is equal to let's say 0. Okay, and second example, d cube y by dx cube, here you can take any constant, plus 3 times let's say y is equal to e to the power x. This is also linear differential equation. Now you might be wondering, sir, where is the dy by dx term? But here we already noted one thing, that the coefficients are constant, so they can be anything, means they can be 0, they can be positive, they can be negative, they can be fraction, right? So here in this second differential equation we can see the term d2y by dx and dy by dx both are absent just because their coefficients are 0, right? Therefore this is the differential linear differential equation, whereas right hand side is a function of variable x, right? Now third example, so let me specify, this is linear, this is also linear. Now let me give you example of non-linear differential equation. So d2y by dx square plus 5 times dy by dx and plus y square is equal to sine x. This is non-linear because we can see dependent variable is y, but its power is more than 1. This is not allowed, right? Now fourth example, d cube y by dx cube plus dy by dx whole square plus y is equal to 2. Now this is also non-linear because we can see second term. Here you can see the second term, power is 2. This is also not allowed, right? So that's why it is non-linear. And now I will take one example where we will have product of dependent variable with its derivative, right? So d2y by dx square plus y dy by dx plus 2y is equal to e to the power x plus sine x. Now we can see this is also non-linear just because this product is involved, y into dy by dx. This is also not allowed, right? So this is also non-linear. Now you came to know that what is the difference between linear and non-linear differential equation with constant coefficients. So by looking at first two examples, we can understand all coefficients are constant, and right hand side it can be function of variable x or can be 0, right? And all the requirements means there should be no product of dependent variable with its derivative, or power of dependent variable has to be 1, and power of differential operators has to be 1. Okay, that is degree. Okay, fine. Now next question in everyone's mind is how to solve higher order linear differential equation with constant coefficients. So let me write the general form. Let us generalize this. The general form of nth order. So order means you can see here in the second example, order we can see 2, 3 is there because 3 times maximum differential operator you have to see in the given linear differential equation. It is this, and its order is 3 because 3 times we are differentiating. Now if you look at the example number 1, I will understand order is 2 because maximum, how many times you are differentiating? So in that's maximum derivative is 2, right? 2 times we are differentiating, so the order is 2. Okay, and degree means what? Whatever the maximum derivative operator you have, look at its power. In case of linear, it's always 1. Okay, but in other, if somebody asks you what is the order and degree of given differential equation, if it is non-linear, in that case you have to specify, right? So in case of linear, it is always 1, right? Now the general form of nth order linear differential equation, nth order linear differential equation with constant coefficients, with constant coefficients. Now let me generalize that thing. So here I'll write a suffix n d n y dx to the power n. Now by default I am assuming y is dependent and x is independent variable. Okay, and just keep that throughout this I will keep this notation throughout this chapter, okay? dy by dx. And plus an minus 1 dn minus 1 y dx to the power n minus 1 plus and so on. Second last term will be a1 dy by dx, last term a naught y equals to f of x, some function of variable x, right? And an minus 1 all are constants, where all this a suffix n, a suffix n minus 1 and a1 comma a naught are constants. Okay, so this is the general form, and if you put particular number of particular value of this n, you'll get the different differential equations, right? And if you put particular values of constants, you'll get the particular differential equation, right? In fact, by putting f of x as well. So now, why we are writing general form? Because we want to deal with some different cases by getting the auxiliary equation. So it will look like a polynomial if you use the notation. So put d by dx is equal to capital D. So that D stands for derivative operator, right? And now what I'll do, I'll just replace, let me call this as the equation number 1. So in equation number 1, I'm going to replace everywhere the term d by dx by capital D. And so if d by dx is equal to capital D, then I will say d2 by dx square. This operator will be d square. D cube by dx cube is equal to d cube, and so on. So everywhere I'm going to replace in equation 1. So therefore equation 1 becomes, therefore equation 1 becomes as a suffix n constant. I will keep as it is, okay? First constant here we can see a suffix n as it is. Now here we can see d to the power n, that's why it will be capital D to the power n, and y I'll keep as it is, okay? No change in the y. And second term you can see in equation number 1, second term a suffix n minus 1. Now we have power n minus 1, right? So capital D to the power n minus 1, y as it is, and so on. And now we can see this term a1 as it is, and now we have dy by dx, it is simply capital D times y, and plus constant, last term you can see a naught y as it is, and right hand side f of x, okay? What I did, I just replaced d by dx by capital D and respective values of d2y by dx square, d cube by dx cube, and so on. In equation 1 I get this equation. Now what I'll do, I'll just take y common at left hand side, so therefore it will be a suffix n plus a suffix n minus 1 and so on, plus a suffix 1 plus a suffix naught, bracket complete, and y is equal to f of x. Okay, fine. Now what I'm going to do for our convenience, I'm going to call this term which is in bracket, I'm going to call this term as a, just for sake of convenience, okay? So let phi of d, so let phi of d, yes.
So what about the D term?
Sorry, I forgot that. Here we have d as well.
Okay, sir. Understood.
Yeah, let me write it. D power n, and here n minus 1, d to the power n minus 1. The derivative operator is there as it is. A1d and last term a naught. I have just taken y common and all the remaining terms inside the bracket, and now I'm going to call this as phi of d. So a suffix n d to the power n plus a suffix n minus 1 d to the power n minus 1 and so on. So second last term a1d plus a naught. Okay, now here onward we are going to deal with the solution. So the shortest form we obtained here, let me call this as the equation number 2. And so if you let phi of d as this thing a and d to the power n and so on, and then putting this value back to the equation number 2, so the equation 2 will become, or it will look like a phi of d, and that outside there is a y, that term as it is equal to f of x. Now this is the shortest notation we have to denote nth order linear differential equation with constant coefficient. So whenever I write phi of d times y equals to f of x, you have to understand this is nth order linear differential equation with constant coefficients where phi of d is this much. Okay. Now the next question is, now next term I want to define, it is homogeneous linear differential equation. Now what is homogeneous linear differential equation? So very simple. If f of x is equal to 0 for any value of x, then let me call this as a 3. Then equation 3, therefore phi of d times y equals to 0. So such an equation, phi of d times y equals to 0, called as homogeneous linear differential equation, right? Differential equation. So here we can see at right hand side we have explicitly 0 number. Okay, and if f of x is not equal to 0, then you can say this is just a linear differential equation with constant coefficient, or you can say non-homogeneous because right hand side is not equal to 0. Okay, otherwise it is homogeneous. And now we are interested in solving how to solve homogeneous linear differential equation, and thereafter we will go for a non-homogeneous linear differential equation its solution, right? So first we will deal with this homogeneous part. So the first part, phi of d times y equals to 0, right? Now here phi of d times y equals to 0. So what we will do, if you let y equals to 0, then we will get nothing, means only y equals to 0, that's okay. But do we have any non-zero solution? For that purpose, what we have to do, we have to let, or we have to equate phi of d to 0, right? And therefore what we have, phi of d equals to 0 means what? We have earlier we have this polynomial in terms of d, you can see here, right? And so let me write that as it is. So therefore a suffix n d to the power n plus a suffix n minus 1 d to the power n minus 1 and so on, plus a1 d plus a naught equal to 0, right? And now we can see if there is a polynomial and we are equating it to the 0, that means we are interested in finding the values of d in this case. So if you change the notation, it will look like a suffix n m to the power n plus a suffix n minus 1 m to the power n minus 1 and so on. So our aim is to find the roots, right? To find the solution of this equation. And once you get the roots, then thereafter you can write the solution accordingly. Okay, so let me explain this with the help of particular case. Okay, and then we will generalize it. So let me take differential equation, solve. So we are dealing with the homogeneous part. Later on we will deal with the non-homogeneous part where we have right hand side as a non-zero function. Okay, so solve dy by dx minus 2 times y equals to 0. Okay, now our aim is to solve this differential equation. Now you will say, sir, we can do the variable separable and then we can have the solution. Okay, so let's do it with the help of variable separable and then I will explain you. No need to solve it by variable separable. Okay, so solution dy by dx is equal to 2 times y, and now what I will do, I'll separate the variables. So therefore we have dy upon y is equal to 2 times dx. Now this is in variable separable form, right? In variable separable form. And now integrate on both sides. So therefore integration of dy by y is equal to 2 times integration of dx plus constant c. And now we can see here, what is the integration of this 1 upon y? Yes, anyone?
Log y.
Right, it is log y and it is equal to 2 times x plus constant c as it is. Now I'll take exponential on both sides, right? So therefore e to the power log that will get cancelled to each other, so we get y is equal to e to the power 2x plus c. And now what I'm going to do, I'm going to solve it further. So e to the power 2x into e to the power c, and then I will call this e to the power c as another constant, let's say k. So we have k, or let's say c1. So c1 times e to the power 2 times x, where that c1 very complicated constant we have e to the power c. Okay, this is just a constant. So we obtain y, therefore y is equal to c1 e to the power 2x, and this is the required solution of the given differential equation. Now I don't want to use variable separable method because it is not applicable to each and every example. Okay, and what about if we deal with the higher order differential equation? So for that purpose, I'm going to use little different method. So let's see what I'm going to do. So given differential equation, not that, given that dy by dx minus 2 times or minus 2 times y is equal to 0. Now what I will do, as usual, our notation we used earlier, let d by dx is equal to capital D, right? And therefore let me call this as a 1. So therefore equation 1 will look like, after using this notation, it is d times y minus 2 times y as it is equals to 0, right? I just replace d by dx by capital D. If there are higher terms, then you can replace it by d square d cube, respective values of d, right? And now we can see we have to take the y common, so therefore d minus 2 times y equals to 0. And now to get the non-zero solution, we have to equate the term which is in bracket. So therefore equating, therefore d minus 2 equal to 0. So therefore d is equal to 2. And now we have to write the solution. Once we get the root, we have to write the solution in powers, in powers of e to the power of e, means whatever the roots you are getting, that you have to treat as a power of exponential term. Okay, so here we get one root, d is equal to 2, and the solution we have to write as y depends on x, so y is equal to constant, order is 1, that's why one constant you have to take there. So let's say constant c1 and exponential term, and its power you have to write that root. Okay, so 2, and independent variable, it depends on x, so this is x. Now we can see the solution directly we obtain here, it is y is equal to c1 e to the power 2 times x. And now you can compare this solution with the solution we got earlier by variable separable method, both are same. Okay, so what is the algorithm? The algorithm is very simple. If you are provided with the homogeneous part, let's say phi of d times y equal to 0, then equate this term phi of d to the 0. So phi of d is equal to 0, and let me call this term. This is called as an auxiliary equation. This is called what? Auxiliary equation. And once you equate this to the 0, then a second thing here we have to do, it is roots. Okay, we want to get roots, and once we get the roots, then write the solution in terms of exponential, right? E to the power m1. Let's say we have two roots, then one root, then you have to write c1 e to the power m1x. Now what about if we have two roots, more than one root? Okay, so let me take second example, d2y by dx square plus 2 times dy by dx plus let's say, okay, what about if we have expansion of, okay, d2y by dx plus y is equal to 0. Now what about this differential equation? What will be the roots that we have to compute, right? But you will get the repeated, so I don't want the repeated root. So what I'll do, I'll just want real and distinct root. So I'll just form this way: d minus 1 and d minus 2 times y. So if you write in terms of differential equation, it will be d square minus 2 times minus 3 times d plus 2 times y. So okay, fine. And now let me go back. I'm just going in reverse way. Okay, so here we have d2y by dx square minus 3 times dy by dx plus 2 times y is equal to 0. So start with this one. Okay, so this is the given differential equation, and we are interested in finding the solution of this differential equation. Okay, so what we have to do, we have to use the notation capital D. So therefore, after using the notation, it will be like this: d square times y minus 3 times dy plus 2 times y as it is equals to 0, right? Now take the y common, so therefore d square minus 3 times d plus 2, and outside we have y equals to 0. And now equate the term which is inside the brackets to the 0. So therefore d square minus 3 times d plus 2 equals to 0, and we are calling this term as auxiliary equation. Auxiliary equation. So this is the new concept we have. Auxiliary equation means phi of d equals to 0, called as auxiliary equation. Okay, and now our aim is to find out the values of d. This is just a quadratic equation, right? Now how to get the values of d? Yes, any idea? You have a number of choices. Means you can do factorization, you can use quadratic formula, or you can use calculator as well, right? So anyone, how to get the roots? Factorization, right?
-1 -2.
Right. So here d square term as it is, we want the product 2, and the subtraction, their addition has to be minus 3. So d square, okay, fine. D square, then I can write this way: minus 2d minus d. Okay, just splitting this minus 3 as minus 2d minus d, and this plus 2 as it is equals to 0. And now we can take d common from first two terms. So d minus 2, and we can take minus common from the last two terms. So taking minus common, it will be d minus 2 is equal to 0. Now we can take d minus 2 common. So therefore d minus 1 and d minus 2 we have equals to 0, and therefore d is equal to 1, 2. So these are the two roots, and once you get two roots, then you have to write the solution as, therefore y is equal to, corresponding to first root, we have to write this way: c1 e to the power that root, first root, 1 times independent variable x, plus c2 times e to the power second root, that is 2x. Okay, so this is the solution of given homogeneous differential equation, and we call this differential equation as what? Complementary function. Okay, so two things we learn. One is auxiliary equation, and second is complementary function. So what do we mean by complementary function? It is the solution of homogeneous differential equation, that is phi of d times y equals to 0. So wherever we find the solution of homogeneous differential equation, we are going to call that as a complementary function. Okay, so now let me explain with the help of another example, so you'll get the idea. Okay, fine, this is fine. So what is the first case? So first case is that case number 1. If phi of d times y is equal to 0 is given differential equation, then what is the algorithm then? And let's say and this is by default you have to assume this is a nth order differential equation. Okay, and m1 comma m2 comma m suffix n are real and distinct roots of phi of d means phi of d means auxiliary equation, right? Now you are quite familiar with the auxiliary equation. Phi of d equals to 0 called as auxiliary equation, right? And after that we are finding the roots, so you get the idea. So m1 m2, and why I'm writing m suffix up to m suffix n, because in general we are assuming this nth order. If it is second order, then you will get two roots. If it is first order, you will get one root. Third order, you will get three roots. Depends on order. So how many roots we have, it depends on order of that differential equation, right? So in general we have nth order, that's why I'm writing the roots up to m suffix n, and all are real and distinct. So what do you mean by real and distinct? So we don't have any imaginary part, and that's why they are real, but they are not equal. Means we don't have something like this, d is equal to 1 comma 1 comma 2. No, this is not the case, because 1 is equal to 1. We have repeated roots, so this is not the case. We have all roots distinct from each other, right? And then in this case, then solution, then y can be written as c1 e to the power first root m1x plus c2 e to the power m2x plus c3 e to the power m3x, and so on. Corresponding to last root, we have c suffix n e to the power m suffix n x in general. Okay, so this is the way of writing the solution corresponding to the roots which are real and distinct. Okay, so this is case number one. Now I want to explain to you what about, let me explain the second case with the help of example. Second example I want to solve. So let's solve d minus 1 whole square y is equal to 0. So in our traditional notation, if I write this, it will be like this. So if I expand this, so therefore it will be d square minus 2 times d plus 1 y is equal to 0. Okay, and let's say our given differential equation is this, d2y by dx square minus 2 times dy by dx plus y is equal to 0. And after that we have, after that we have this, right? Because in terms of capital D, and our question is start here. Solve. Okay, so after using the notation capital D, I got this term d minus 1 whole square y is equal to 0. After that I just expanded this. No need to expand actually, because we are interested in finding the roots. Now equate this, the term which is inside the bracket, or you can say the coefficient of pi. So therefore d minus 1 whole square is equal to 0, called as auxiliary equation. And after that find out the roots. So can you tell me the roots in this case? What will be the roots?
Plus 1.
Only plus 1?
Yes, sir.
Only plus 1, but you have to say 2 times. Means you can see here, if I write this way, d minus 1, therefore d minus 1 into d minus 1 is equal to 0. So we have, therefore d minus 1 is equal to 0, or d minus 1 is equal to 0, and therefore d is equal to 1, and from this second case also we get 1. So root is only 1, which is 1 but repeated, right? So this is the second case, we have roots are repeated. Now in this case, how do we are going to write the solution? So in this case, little change we have to do. See, in case of repeated root, we have to write the solution as y is equal to, as we noted earlier, that if you get one root, then corresponding to that we have to write this term c1 e to the power that root. Let's say here we have 1 times x. Okay, and if you get second root, then you have to write this way. So here second root is also 1, then corresponding to that c2 e to the power that root. But if I solve it further, what I'll get c1 plus c2 e to the power x. Okay, and now I can replace that c1 plus c2 by another arbitrary constant, let's say c3. So it will be like this, c3 e to the power x. Oh, there is a problem. What is the problem? The problem is that order of the given differential equation is 2, but in case of solution, we are getting only one arbitrary constant, which is C3. So the way of writing the solution in case of repeated root is not correct. Okay, so we have to do little different thing while writing the solution in case of repeated root, and that little change is here. Okay, so instead of writing this way, we have to write corresponding to the second term, we have to write x times, so c2 x times e to the power x. Okay, so this way we have to write the solution. So if you have repeated roots, first root 1, then corresponding to that c1 e to the power that root times x, and plus c2 times, do not write as it is e to the power that root times x, write c2 x times e to the power x. Now let me generalize this. So if what about if we have three repeated roots, let's say 1 comma 1 comma 1, then in that case we have to write the solution as y equals to c1 e to the power x plus c2 x times e to the power x plus c3 e to the power, now c3 times what? We have to raise the power, so power of x, so it is x square e to the power x. That way we have to write the solution. Now let me take another roots so that you'll get the feeling of repeated and distinct root. Okay, so let me take one example. So d minus 1 whole square and d minus 3 y is equal to 0. So suppose this is a given differential equation and I want to solve this for y. Okay, so this is, of course, this is homogeneous as right hand side is 0. Now our aim is to find out the roots. Okay, so we will equate the coefficient of y to the 0. So therefore d minus 1 whole square d minus 3 is equal to 0, and therefore d minus 1 whole square is equal to 0, or d minus 3 is equal to 0, right? Now from the first factor, can you tell me the roots from the first factor? Yes,
1 comma 1.
right. So right, therefore d is equal to 1 comma 1, and from the second term we get d is equal to 3. So total roots, we have 3 roots because order is 3. We can, order means highest power we can say of that differential operator, right? And here we get d is equal to 1 comma 1 comma 3. Now in this case what we have to write? So how to write the solution? In this case you have to write the solution y is equal to, just follow the previous two cases, means corresponding to the repeated root you have to follow the case number 2. So c1 e to the power x, but root is repeated, therefore c2 x e to the power x, and third one is the distinct from the previous two, right? And corresponding to that you have to write the as it is c3 e to the power 3 times x. Do not write x cube, okay, because it is distinct, right? And so this is the way of writing the solution. So let me summarize first two cases what we did. If we have, so let me summarize and then we will go for next case. Okay, so given differential equation, given phi of d times y is equal to 0, and now case number 1, we are looking for the solution of this kind of differential equation. So case number 1, oh, case number 1, if m1 m2 up to m suffix n roots are real and distinct, then y is equal to c1 e to the power m1x plus c2 e to the power m2x plus c3 e to the power m3x, and so on. Last root we have c suffix n constant, arbitrary constant, e to the power that root m suffix n x. So this is the way of writing the solution in case of roots are real and distinct. But case number 2, if m1 is equal to m2, m3, m4 up to m suffix n are real and some of them are repeated. And so here we can see m1 is equal to m2. So first two roots are repeated. Now how do we write the solution in this case? So y is equal to corresponding to repeated root. Corresponding to repeated root, you have to write c1 e to the power m1x, but this is repeated, therefore second term you have to write c2x times e to the power that root. It doesn't matter whether you are writing m1 and m2, both are equal now, so it doesn't matter. c2x e to the power m1x, and corresponding to other roots you have to follow the case number 1. So corresponding to m3 we have to write c3 e to the power m3x plus c4 e to the power m4x, and so on, last c suffix n e to the power m suffix n x. Now what about if we have this case? Now if m1 is equal to m2 is equal to m3, and m4 m5 and rest of the roots are distinct, m suffix n are distinct, okay, from each other, and only three roots are repeated, m1 m2 m3, then in that case we have to write the solution as y is equal to corresponding to m1 c1 e to the power m1x. Now this is repeated, that's why c2 times x e to the power m2x, plus this is again repeated, that's why raise the power of x, c2 x square e to the power m3x, or it doesn't matter whether you are writing m2 m3 because all are equal, you can see here, okay. And then corresponding to the rest of the roots you have to follow the case number 1. So this is going to be c4 e to the power m4x, and so on, last root we have c suffix n e to the power m suffix n x. Do you understand first two cases? Yes.
Yes, sir.
Okay, and now let me take some examples, and thereafter we will go for case number 3rd, which will be what? Which will be complex roots, right? So before going to that, so let me check out some examples. Okay, fine. Okay, so here we have example number 1. Solve the following differential equations. Solve the following differential equations. As we are dealing with the homogeneous part, homogeneous differential equation. So right hand side we have 0, and later on we will have non-zero part. In that case, we have a little different thing to do. Okay, solve first. d2y by dx square minus 5 dy by dx minus 6 times y is equal to 0. Now just look at this differential equation, what I'm going to do. So the process is very simple. Consider the differential equation in terms of capital D. So let d by dx is equal to capital D. So therefore we have in terms of capital A, this will be d square y minus 5 times dy minus 6 times y is equal to 0. Now take y common, so therefore d square minus 5 times d minus 6 times y is equal to 0, and now equate the coefficient of y, which is this. So therefore d square minus 5d minus 6 is equal to 0. So what we call this? We call this auxiliary equation, right? Auxiliary equation. And once we get the auxiliary equation, our aim is to find out roots of that auxiliary equation. So we are interested in finding the values of D, right? So this is quadratic equation we have. Now we have choices. You can use calculator, you can use factorization method, you can use quadratic formula as well, right? So it depends on you. So I will prefer to the factorization, and therefore let's do the factorization if possible. So we want product minus 6, and that addition has to be minus 5. So 3 minus 2 will work. Or minus 3 minus 2 will work. No. So can you help me in this? Yeah.
6 minus 1.
6 minus 1 will work, right? Because product has to be minus 6, and then addition will be minus 5, right? So I think minus 6 plus 1 we have
6.
taken. Minus 6 plus 1, right? So therefore d square minus 6d plus d and minus 6 is equal to 0, right? And now so don't worry, if you don't know how to do factorization, then go for quadratic formula. Otherwise, go with the with calculator. Okay, choices you are. And now I'll take d common. So therefore, d in bracket d minus 6 plus 1 times d minus 6 is equal to 0. And now d minus 6 can be taken common. So therefore, d plus 1 d minus 6 is equal to 0. So this implies d is equal to minus 1, and corresponding to this factor we have 6. So we have roots real and distinct. So therefore both roots are real and distinct. Distinct means they are different from each other, and therefore corresponding to the if we have real and distinct roots, then case number 1 tells us that we have to write the solution this way: y is equal to corresponding to the first root c1 e to the power minus 1 times x, because that root you have to write as a power of exponential term, plus c2 e to the power second root 6 times x. So this is the way of writing the solution if we have real and distinct root. So this is the final solution, okay, of the given differential equation. Now let me give you one example and I want to ask you the solution. Before that, I will explain another example where we are going to deal with the some repeated and distinct roots. Okay, fine. Here we have third. Let me take a third order differential equation. So we are interested in solving this differential equation. d cube y by dx cube plus 2 times d2y by dx square plus dy by dx is equal to 0. Now here in terms of capital D notation, I'll write here directly. So therefore we have d cube y plus 2 times d square y plus d times y is equal to 0. Now I'll take y common, so therefore d cube plus 2 times d square plus capital D y is equal to 0, and therefore auxiliary equation it is this: d cube plus 2 times d square plus d is equal to 0. So this is what auxiliary equation. Auxiliary equation. And then once you get the auxiliary equation, our aim is to find the complementary function. Means complementary function means solution of that given differential. This is complementary function, right? Okay, and to find the complementary function we need roots, right? And so we have to solve it for d. So I can see here everywhere d is occurring in each and every term, and therefore I can take it common. So therefore d times in bracket we left with d square plus 2 times d plus 1 is equal to 0. And now we can equate d to the 0 and this term to the 0. So therefore d is equal to 0, or d square plus 2 times d plus 1 is equal to 0, right? And now we can have one root we already got, it is what, 0. Now our aim is to solve this. Now can you tell me how to solve this further? This second term, d square plus 2d, it is what?
D is equal d plus 1 is
Right, this is
1
right. So therefore not 1, actually minus 1 will be root. So d is equal to 0, or now I can see this is just the expansion of d plus 1 whole square, right? D square plus 2d plus 1 is equal to 0, right? Whole square, and therefore we can see therefore d is equal to 0, or d plus 1 is equal to 0, d plus 1 is equal to 0. That will give me d is equal to minus 1 comma minus 1. And so total roots are, so therefore total roots are d is equal to 0, second minus 1, third minus 1. Now in this case, how to write the solution? This is just a mixture of case number 2 and case number 1. It means some roots are repeated and some of them are different, okay, distinct, right? So corresponding to the first root 0, we will write y is equal to c1 e to the power that root 0 times x, okay. Now here we can see minus 1 repeated, therefore corresponding to that term C2 e to the power root that root minus 1 times x, and as it is repeated, that therefore C3 times x e to the power minus x. Now I can solve it further. So e to the power 0 is always 1. So therefore this is simply C1, and C2 I will take this exponential term common. So therefore C2 plus C3x, this is in bracket, and now outside bracket we have e to the power minus x. So this is the solution. Do you understand this example? Yes? Any doubt?
Yes, sir. Clear.
Right? So let me give you some roots, and I want to ask you directly the complementary function. Of course, you have to find the roots and all the process you have to do, but let me check whether you understand this or not. Okay. So for example, if I have roots d is equal to 1 comma 2 comma minus 1. Okay, so now directly tell me complementary function, yeah, corresponding to these three roots.
Y is equal to C1 e to the power 1x plus C2 e to the power 2x plus C3 e to the power minus x.
Yes, very good, this is correct solution. Okay, corresponding to roots are real and distinct. Now let me change a little bit here. Now tell me 1 comma 2 comma 2 comma 1. So if suppose this is the case, then how to write the solution?
Y is equal to C1 plus C2x whole outer bracket e raised to power 1x. Then again plus bracket start C3 plus C4x bracket close e raised to power 2x.
Very good, very good. So you understand this, very good. And now if we have another case, let's say d is equal to minus 1 minus 1 minus 1, and they can be rational number 1 by 2 and root 2. Suppose this is the case, then y is equal to
C1 plus C2x plus C3x square whole inside bracket e raised to minus x plus C4 e raised to x by 2.
X by 2 or 1 by 2 times x, okay. Yes.
And C5 plus C5 e raised to power root 2x.
Very good. Now you clearly understand first two cases. Okay. Now, okay, fine. Later on we will solve some different examples. Okay. So let me tell you about. Let me explain third case by starting by giving one example. Okay. So here we have another example. Solve d square plus 1y is equal to 0. Okay, now I want to solve this differential equation. So process is same. Find out auxiliary equation and then equate it to the 0. Auxiliary equation means by default we have equal to 0, and therefore after that, once you get auxiliary equation, find out roots. Okay, so here what is the auxiliary equation? Can you tell me directly? What is the auxiliary equation?
D square plus 0d plus 1 is equal
d
to
square
0.
Right, d square plus 1 is equal to 0. So this is the auxiliary equation. And so what will be roots? Can you solve it?
Plus 1 minus 1.
This is not the case. Is it plus minus 1?
Mixed roots.
Imaginary.
Imaginary, very good. Imaginary, complex roots we have. Now let me explain this why we are getting complex roots. Now you know, you are quite familiar with the quadratic formula, right? So if you have ax squared plus bx plus c is equal to 0, then roots are given by x is equal to minus b plus minus square root of b square minus 4 times ac divided by 2 times a, right? And now just compare this. Instead of x we have d here, right? So therefore here coefficient of d square it is 1, so the value of a it is 1, and coefficient of d is absent, therefore coefficient of d it is 0, so b value we have 0, and last term constant c we have here 1. Okay, now put all these values in this formula, and therefore instead of x we will have here d. So d is equal to minus b, that is minus 0, plus minus square root of b b square. What is b square? 0. 0 square is 0. Minus 4 times AC. So 4 times 1 into 1. Right? 4 times 1 into 1. And whole divided by 2 times a. So 2 times a means 1. Okay, now solve it further. So therefore d is equal to plus minus, and here we have root of minus 4 divided by 2. Oh, root of minus 4. In that case, what we have to do? What we have to write? It is imaginary. So therefore it is plus minus root of 4 I, where I is nothing but the root of minus 1, and this divided by 2 as it is. But what is the value of root 4? It is 2. So therefore it is plus minus 2 upon 2I, and therefore it is plus minus I, and that's why we are getting two roots, but both are imaginary. So therefore d is equal to I comma minus I. Now okay, fine, we are getting the roots, but both are imaginary. Then how to write the solution? The process again same. We have to write y is equal to c1 e to the power first root I times x plus c2 e to the power minus I times x. But can we solve it further to get the simplified version of the solution? Okay, so that's the question to think about. Okay, so think over it, and we will see this case in next lecture. Okay, I hope you understand first two cases. Any doubt into first two cases? Yes. Yes.
No, sir.
Yes, sir.
Okay, fine.